Hello, everyone. I'd like to greet everyone who speaks English. Today, we are going to talk about machine learning, and let's proceed to brief introduction of myself. Actually, I do this brief introduction of myself at each lecture because, I do hope that you will watch all the lectures, but maybe you are somehow familiar with the content of the video lectures provided within the framework of the machine learning course, and maybe you are willing to watch only one lecture. For this reason, I provide a very short presentation of myself. Okay, my name is Stanislav Hiroshenko. I represent Ural Power Engineering Institute of Ural Federal University, and I am your lecturer of machine learning and artificial intelligence. Within the framework of today's lecture, we will focus on the main concepts behind machine learning and artificial intelligence, including data, information, and knowledge. And we are going to focus on what is the main difference between information, data, and knowledge. Moreover, we will consider different types of knowledge, and this will help us to map the problem under consideration. I mean the problem within the framework of summer school project case, and define the relations, I would say types of knowledge, and maybe ways to transform different data in order to achieve more effective solution. So we will talk briefly about intelligence systems and their types, and I will focus your attention on information systems application in power industry. And in the next part of the lecture, we will talk about different types of machine learning methods, splitting the data set in order to apply machine learning methods. And the last, but I would say maybe not the least, maybe the first in terms of importance, topic of the lecture will be devoted to evaluation metrics for machine learning. It's like measuring the quality of machine learning algorithms. Let's start our today's video lecture with a short talk about intelligence systems. Actually, data are recorded facts. They can be presented in forms of symbols, signs, words, numbers, figures, whatever. Arithmetic and logical data processing makes it possible to obtain information. But information, if necessary, can become data again if further processing is required for another process. The next stage of information conversion is knowledge. Knowledge is information that has been processed and analyzed many times and can be used to make decisions. Actually, knowledge may be of two types, formal and informal. Formal knowledge can be described in the form of standards, instructions, documents, guidelines, whatever. Informal knowledge is experience, impressions of specialists in a specific subject area. Often the terms data, information, and knowledge are used synonymously. The meaning, however, is not the same. In the basic form, data are different symbols and characters whose meaning only becomes clear when they are connected with context. Collecting and measurement observations generates data. Usually machines send, receive, process data. The confusion between data and information often arises because information is made out of data. Data reaches a more complex level and becomes information by integrating them to a context. Information provides expertise about facts or objects. For example, the information about manufacturing date of the power transformer has very little value when it is unknown to which particular transformer it belongs. By adding more information like the model, voltage, rated capacity, the linked information creates knowledge about power transformer. Knowledge then describes the collected information that is available about a particular fact or an object under consideration. The knowledge of this situation makes it possible to make informed decisions and solve the problems. Uh, Thus, knowledge influences actions of people, actions of decision makers. Machines can also make decisions based on new knowledge generated by information. In order to gain knowledge, it is necessary to process information. Wisdom. Well, wisdom is the top of the hierarchy, and to get there, we must answer the questions such as why to do something and what is the best. In other words, wisdom is knowledge applied in action. We can also say that if data and information are like look back to the past, knowledge and wisdom are associated with what we do know and what we want to achieve in the future. Let's consider a simple example and diversify data, information, knowledge, and wisdom. Well, first, data. Let's assume that the traffic light turned red. Yep. So, what do we consider as data? So, it's the red color of the traffic light, maybe some figures associated with signal routing of the traffic light integrated into the communication network, some other data. So we just have some facts regarding the object under consideration. If we add some meaning, let's say that south-facing traffic light on the corner of Pitt and George Streets has turned red. This is treated as information because we are analyzing data in context. So we just took the initial measurements, color, some roads, yes, and applied to the particular address. So we know this data in context right now. Let's move on to knowledge. Knowledge is information in context. The traffic light I'm driving towards has turned red. So this is the judgment regarding the current situation. So you are driving the car and the traffic light you are driving towards turned red. And finally, we jump to wisdom. Wisdom is applied knowledge. At this stage, you know what to do because you'd better stop the car if the traffic light turns red. Knowledge may be of different types. Knowledge representation is such a process which depends on the logical situation and enables a strategy to take a decision in acquiring knowledge. There are many types and levels of knowledge acquired by human in daily life, but machines find it very difficult to make interpretation of all types of knowledge. For such conditions, actually, knowledge representation is typically used. Now let's consider different types of knowledge based on the industry example of the power transformer. Well, actually, let's start with declarative knowledge. It is a segment of knowledge which stores actual information in a memory, and this type of knowledge seems to be static in nature. These can be things or events or processes, and the domain of such knowledge is to find the relation between events and things. Let's move forward to procedural knowledge. This knowledge is less general compared to declarative knowledge and is also called imperative knowledge. It can have the potential to declare the accomplishment of a particular process, of a particular thing. For example, if we take guidelines, instructions, standards, practically can be referred to as procedural knowledge. Heuristic is also known as shallow knowledge, and it follows the principle of thumb rule. It is very efficient in reasoning process and it solves the problems based on the records of past problems or the problems which are compiled by experts. It provides knowledge based on the experience it gathered during the past problem solutions. Meta-knowledge. These types gives an idea about the other types of knowledge that are suitable for solving the problem. It's like knowledge about the knowledge. Meta-knowledge is helpful in enhancing the efficiency of problem solving through proper reasoning process. Structural is the most basic knowledge, and actually it's typically applied to problem solution process. It tries to find out relationship between concepts and objects. Structural knowledge is associated with the information based on rules, sets, concepts, and relationships. It provides the information necessary for developing the knowledge structures or some sort of overall mental model of the problem under consideration. Well, now let's turn to different areas of artificial intelligence application. And the first one to draw your attention to is neurocybernetics. It's about creation of the thinking artificial device which reproduces the structure of human brains in some way. This actually how neural network does. The next one is black box cybernetics. Actually, the background for black box is no matter how the device is arranged, it responds to input actions in the same way as human brains. So it's like algorithms of the existing computers, logical, which are based on rules. And the last but not the least one is human-machine systems, which are interactive, intelligent. They interact with the environment to achieve the stated goals for a specific problem under consideration. Um, Now let's formulate the definition of the intelligent system. Actually, what is it? Intelligent system is an automated system based on knowledge or a set of software, linguistic, mathematical tools to perform the main task of implemented the support of human activities. If we specify the major characteristics of the intelligence system, first of all, intelligence systems have developed communication skills. So it is possible to, for example, formulate a spontaneous request in a form of a dialogue in a natural language and to get the feedback. The second feature is ability to solve complex, poorly formalized problems. Actually, this point requires the original solution algorithms because the majority of the poorly formalized problems are characterized by uncertainty or great dynamics of the initial data and knowledge that we have. The next feature is unsupervised learning ability. Actually, it's one of the main features because when you create the intelligence system and implement it at industry facilities, it is really expected that in subsequent years, this system is going to be smarter. So it means that the system is able to automatically extract knowledge for solving problems from the accumulated data, from the accumulated experience. And the last one is adaptability. Actually, it is the ability to develop system in accordance with the changes of the objectives or the problem statement. It means that sometimes the problem under consideration is characterized not just by the changes of the input data, like it can be observed in case of photovoltaic power plants forecasting, but it changes from the point of view of the structure of problem statement. And intelligent system is required to support, yes, and to provide the solution for such changes. In this slide, we see different types of intelligence systems with the properties specified previously. For example, the systems with communication skills, intelligent database, they differ from the usual ones by the opportunity to provide process information, which may not be explicitly stored in this specific database. But anyway, these databases provide output from the existing data. Natural language interface systems assume the translation of natural language constructions to machine level of knowledge representation. In this case, the recognition and verification of the written words is carried out according to dictionaries and syntactic rules. This interface facilitates access to intelligent databases as well as voice input of commands in control systems. Hypertext systems are designed to search for textual information by keywords in databases. Contextual help systems are usually some sort of a special case of hypertext and natural language processing systems. Cognitive graphics systems allow the interaction of the intelligent information system user through the icons. The same goes for experts, unsupervised, and adaptive systems as well. They have various implementation areas and they are subjected to the corresponding requirements. Anyway, regardless of the type of the information system, in generalized form, the system is implemented by creating the following main subsystems. Then data handling begins with its collection and pre-processing. Once in a database, other algorithms can deal with this data, including algorithms for feature extraction and algorithms for knowledge extraction using machine learning approaches. The output subsystem with which the user interacts deserves special attention because it is required to provide the data, the information, in a user-friendly, understandable way. As examples of industry problems solved by intelligence systems, it is worth noting the automated dispatch control of power systems, including the problem of power system state estimation, based on incomplete measurement data acquired from various monitoring and electric energy accounting systems installed throughout the area, the territory of the power system. Another important class of problems is associated with planning technological process, forecasting the load and renewable generation. And finally, the previously considered example of the problem, like power equipment technical state assessment. The presented examples of problems and intelligence systems are united by the feasibility of obtaining a solution even in case of incompleteness and low quality of the initial data. Now let's talk a little bit in more detail about machine learning. Let's start with the terminology. Since the concepts of artificial intelligence, machine learning, artificial neural networks are not always clearly separated. Artificial intelligence is the highest level of abstraction. So this term generalizes methods, algorithms, technologies, research for solving problems that have some creative intellectual component, problems for which there are no clearly defined algorithm for obtaining the exact solution. In particular, if there is such a problem and initial data, and there is no algorithm for its solution, then we can say that machine computer itself has learned how to solve it. And it is the exact place when machine learning starts acting. Unfortunately, a miracle will never happen, and the machine will not learn anything if you do not set for it a knowledge representation model and an algorithm for the formation of this model, that is, a learning algorithm. One of the most important concepts of machine learning is the apparatus of artificial neural networks, based on the principles of the human brain. And finally, deep learning corresponds to the types of neural networks models. Now I want to note only deep neural networks that shows impressive results in speech recognition, machine translation, image recognition tests. Even as we speak, these models are closely related to our lives, although we usually do not think about it. In general, the principle of deep learning itself can be applied not only to neural networks. It is based on the hierarchical extraction of knowledge from the dataset, from the simplest features, point, gradient direction, number of complex abstract concepts like image of a car, questions, equipment state, whatever. Now let's look at the machine learning relationship in context. It is closely related to data, algorithms, including algorithms specific to the subject area, and computer technology in general. Data plus algorithms enable us to extract new data or knowledge from the dataset. The data-focused part of computer science is called data science. It is an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data, and apply knowledge and actionable insights from data across a broad range of application domains. If we take computer science and algorithms, principles, rules of the subject area, then we can form a set of relevant features for the problem being solved. Choosing informative, discriminating, and independent features is a crucial element of effective algorithms in pattern recognition, classification, regression, any possible task within the framework of machine learning. To apply machine learning, it is necessary to have competences in all the specified areas. Now let's turn to different basic concepts of machine learning. And we are going to start with supervised learning as one of the most widely spread and most popular machine learning concepts. Okay, so supervised learning is defined by its use of labeled datasets to train algorithms to classify data or predict some outcomes accurately, like in case of photovoltaic energy prediction. As input data is fed into the model, input row dataset. So the model adjusts the weights until it has been fitted appropriately, which occurs as part of the validation process. Supervised learning helps organizations to solve a variety of real problems at scale, such as classifying spam, identification, technical state of power equipment, defining the weather type within the framework of the dataset for PV output forecasting. Supervised learning uses a trained set to teach models to get the desired output. This training dataset includes inputs and correct answers, which allow the model to learn over time. The algorithm measures its accuracy through the loss function, adjusting until the error has been sufficiently minimized. Supervised learning can be separated into two types of problems when data mining. It's classification and regression. Classification uses an algorithm to accurately assign testing data into specific categories or classes. So it recognizes specific entities within the dataset and attempts to draw some conclusions on how those entities should be labeled or defined within the framework of a particular class. Common classification algorithms are linear classifiers, support vector machines, decision trees, k-nearest neighbor, random forest. Actually, they can be easily found in the corresponding literature. The second fundamental task is regression. It is used to understand the relationship between dependent and independent variables. It is commonly used to make projections, such as for sales revenue for a given business, like projection of the photovoltaic energy output. So the problem within the framework of the project case is purely a regression one. Linear regression, logistical regression, polynomial regression are very popular regression algorithms. Anyway, you may use many other like SVR, decision tree regressors, etc. Now let's be a little bit more specific about unsupervised learning. It uses machine learning algorithms to analyze and cluster unlabeled data sets. These algorithms discover hidden patterns or data groupings without the need of human intervention. Actually, its ability to discover similarities and differences in information make it the ideal solution for exploratory data analysis, like customer segmentation, image recognition, whatever. Unsupervised learning models are utilized for three main tasks: clustering, association, and dimensionality reduction. Clustering is a data mining technique which groups unlabeled data based on their similarities or differences. Clustering algorithms are used to process raw, unclassified data objects into groups represented by structures or patterns in the information. Clustering algorithms can be categorized in a few types, specifically exclusive, overlapping, hierarchical, and probabilistic. Association rule is a rule-based method for finding relationships between variables in a given dataset. These methods are frequently used for market analysis, allowing companies to better understand relationships between different products. Understanding consumption habits, including the consumption habits of electrical energy consumers, enables businesses to develop better cross-selling strategies and recommendations. Examples of these can be the Amazon's customer who bought this item also bought this, or Spotify Discover Weekly, or maybe, I don't know, like Apple Music playlist, whatever. And the last but not the least is dimension reduction. While more important data generally yields more accurate results, it can also impact the performance of machine learning algorithms, for example, in terms of overfitting. And it can also make it difficult to visualize datasets. Dimensional reduction is a technique used when the number of features or dimensions in a given dataset is too high. It's like you have, I don't know, like tens, hundreds of features. It reduces the number of data inputs to a manageable size while also preserving the integrity of the dataset as much as possible. So it is commonly used in the pre-processing data stage when you have this multiple feature set and you get maybe a couple of features but which are more important from the point of view of the information content, and it doesn't distort or degrade the performance of the machine learning algorithm. And the last but not the least is reinforcement learning. Actually, in reinforcement learning, an artificial intelligence faces a game-like situation. The computer employs trial and error to come up with a solution to the problem. To get the machine to do what the programmer wants, the artificial intelligence gives either rewards or penalties for the action it performs. Its goal is to maximize the total reward or benefit. Although the designer set the reward policy, that is the rules of the game, so he gives the model no hints or suggestions so how to solve this problem. It's up to the model to figure out how to perform the task to maximize the reward, starting from totally random trials and finishing with sophisticated tactics and superhuman skills. By leveraging the power of search and many trials, reinforcement learning is currently the most effective way to hint machines' creativity. In contrast to human beings, artificial intelligence can gather experience from thousands of parallel gameplays if a reinforcement learning algorithm is run on the sufficiently powerful computer infrastructure. So actually it reflects the way how the human beings are being learned, and it is one of the most advanced technologies to train the machine learning model. Let's consider the examples from the power industry. The most important here are supervised and unsupervised learning ones. For unsupervised learning techniques, let it be clustering, which may be used for identification of the group of the defects, for example, in a faulty equipment, or identification of some preliminary unknown subtypes of weather conditions when you are dealing with photovoltaic power plants forecasting. Dimension reduction is, for example, transformer failure analysis, when you get the more generalized knowledge and reduce the number of features to perform the diagnostics. Association corresponds to the problem of analysis of the elements which are prone to failure. Actually, it is very important from the point of view of scheduling and planning of service and maintenance. Supervised learning approaches categorized into classification and regression. And actually, what stands for classification is classification as power transformer technical state. And regression is when you have the task of predicting the technical state of the power transformer in some like time horizon, maybe in a month or in a year. As it was noted many times, machine learning is impossible without data. Actually, data is the basics, is the foundation for all the machine learning algorithms. So you can't just feed all the data into the model, because if the model is trained, set up, and validated on the same data, it is very easy to get a fit. A statistical model or a machine learning algorithm is said to have underfitting when it cannot capture the underlying trend of the data. Let me see here. A statistical model is said to be overfitted when we train it with a lot of data. It's here. Actually, in case of overfitting, model gets trained with so much of data, and it starts learning from the noise and inaccurate data entries in our data set. Then the model does not categorize the data correctly because of too many details and noise. So we have to align ourselves with the happy medium. And so we just try to find out not too complicated, but not too simple model to fit the process, to fit the challenge that we aim to find the solution. Okay, so within the framework of data preparation, you need to split the data sample into parts, at least into training and testing set. Actually, it is preferably into the training one for training, the validation one for preliminary assessment, and model parameter setting, and the test one for final objective testing. The portions of division depends on the amount of data and their variety. Usually 10–20% is allocated for testing. But let me give you a couple of hints dedicated to preparation of the training set for the task of photovoltaic power plants forecasting. Of course, power plants that use the energy of sun are naturally installed in the areas, in the regions where there are lots of sunny days. For this reason, maybe you have noticed it from the initial data sample, about 90% of the data samples represent normal sunny weather conditions. And it's very important because if you will not treat the formulation of training and testing set properly, finally you will get the model which perfectly predicts sunny weather conditions, but it will never be able to predict cloudiness. And for this reason, well, please think about the shares of sunny, cloudy, rainy data in the training set and in the testing set to be sure that your model is able to predict photovoltaic power plant output in abnormal conditions. So, in relation to the previous slide, if the sample, I mean the data sample, is not very large, then the allocation of training, validation, and testing sample may affect the result. To prevent this from happening, training and validation set can be mixed using the procedure called cross-validation. At each iteration, a part of the sample is used for training and a part for validation. The results obtained are averaged. In sum, all the elements of the sample at one or another iteration will be in the validation set. Now let's consider the quality metrics of machine learning models. Actually, they differ depending on the types of the problem under consideration, like classification, regression, or clustering. Well, for classification problems, metrics in different ways take into account errors when model assigned an object to a wrong class. So it can be referred to as misclassification. Actually, it's a confusion matrix, error matrix, accuracy, precision, recall, ROC curve, F1 score, and many other metrics which could be applied to merit the quality of the classification models. For regression problems, the metrics differ in the principle of taking into account the deviation of the model result from the true one. Among the most popular metrics are mean absolute error, mean absolute percentage error, R2 score, root mean squared error, mean squared error, like normalized mean squared error, etc. So you may have multiple other metrics within the framework of dealing with regression models as well. For clusterization models, the quality metrics are not so evident. Well, actually, as far as there are no correct answers for clusterization problems, the assessment of their effectiveness is more difficult and highly dependent on the specifics on the problems under consideration. But anyway, the majority of the clusterization models metrics measure the distance between the allocated clusters, groups of objects, to get the idea of the quality of the result of clusterization procedure. Well, as far as classification is one of the most widely used problems in machine learning with various industrial applications, from face recognition, content moderation, like power transformer, technical state assessment, um, text classification, etc. There are various ways to evaluate a classification model. And within the framework of our lecture, I will cover some of the most popular. Confusion matrix. Actually, confusion matrix is not a metric, but it's very important to know. One of the key concepts in classification performance is confusion matrix, which is tabular visualization of the model predictions versus the ground truth labels. Sensitivity and specificity are statistical measures of the performance of a binary classification test that are widely used. Sensitivity, its true positive rate, measures the proportion of positives that are correctly identified. In other words, the portion of those who have some condition who are correctly identified as having this condition. Specificity, true negative rate, measures the proportion of negatives that are correctly identified. In other words, the proportion of those who do not have the condition who are correctly identified as not having the condition. A receiver operating characteristic curve, or ROC curve, is a graphical plot that illustrates the diagnostic ability of the binary classifier system. Logarithmic loss, or log loss, works by penalizing the false classifications. It works well for multi-class classification. When working with log loss, the classifier must assign probability to each class for all the samples. Actually, one important thing to add that typically classification problems may be divided into binary classification like good and bad, and multi-class classification when you have these multiple labels, multiple classes or groups. For example, if we want to classify the action taken by the decision maker when having the faulty equipment, we may say leave an operation, provide additional service and maintenance, or disconnect, yes, and send to the manufacturer's side. So It is multi-class because we have the number of labels more than 2. And anyway, within the framework, even within the framework of multi-class classification, the problem can be transformed into binary classification, which is more simpler to find the correct solution. It's like finding one versus all, because, for example, you want to find leave in operation versus all other actions, or you want to find send to the manufacturer's side versus all other actions presupposed by the introduced scale of the decisions. Confusion matrix, as the name suggests, gives a matrix as output n by n, where n is the number of classes being predicted. Confusion matrix, also known as error matrix. This metric used for finding the correctness and accuracy of the model and even works better for imbalanced dataset. Precision shows the number of truly positive outcomes from the entire set of positive labels identified by the classifier. Recall is the fraction of relevant instances that were classified. Classification accuracy is a metric that summarizes performance of the classification model as the number of correct predictions divided by the total number of predictions. Let's consider the example of defective non-defective states classifier. Based on the figures given in confusion matrix, classification accuracy is observed to be around 92%, which is actually a very high quality result. Defective states recall, which actually means the share of relevant defective states identified by the algorithm among all true defective, is also very high, 90%. But precision, showing the share of true defective among all assigned as defective, is rather low, about 36%. That means the algorithm detects the defective class quite well, but the result also includes points from other class which should be treated in a proper way. Regression quality metrics completely different from the classification ones as far as within the framework of the regression problem, you are supposed to provide a continuous output. Within the framework of regression quality metrics, loss functions are typically used. Actually, loss functions are a type of methods to evaluate how well your algorithm models your dataset. Well, now let's talk in a little bit more detail about possible loss functions for regression problems. And we start with mean absolute error. So MAE measures the average magnitude of the errors in a set of predictions, actually without considering their direction, either positive or negative. It is the average over the test sample of the absolute differences between prediction and actual observation, where all individual differences have equal weight. Actually, it is usually intended to measure average model bias. Mean squared error, maybe together with mean absolute error, tell you how close a regression line is to a set of points. Mean squared error is just like mean absolute error, but squares the differences before summing them all instead of using the absolute value. We can see this difference in the equation at the left side of the slide. Actually, as we can conclude from the formula, MSE assigns more weight to the bigger errors. So the algorithm then continues to add them up and average them. Actually, if you are worried about the outliers in your model, actually this is the metric that you should look at. Root mean square error actually measures the distance between the mean value and the corresponding dots on the function. And if you want to get the squared error, so just square RMSE and get the corresponding result. Just a few words about mean percentage error and mean absolute percentage error. Actually, MPE tells us if there are more positive errors than negative or vice versa. So in order to analyze the behavior of the model, either you underpredict or overpredict the ground truth that you have in the initial data set. Being more specific about mean absolute percentage error, well, from one point of view, this type of metrics is very well understandable by the majority of people because the output of mean absolute percentage error is typically provided in percents. But it's very important to understand what is the background behind MAPE. Actually, MAPE is the ratio of the residual over the actual value. And it's very important what kind of prediction you have. So if your predicted value is smaller than the actual one, typically you get the error not greater than 100%. But if your prediction is greater than the actual value, you may get 100% error and more, even 200% error, 300%, etc. So as far as you are calculating mean absolute percentage error, so these types of error outliers, I would say like that, will significantly distort the overall accuracy of the algorithm that you are testing. Well, now let's me turn your attention to the project case example. Um, in this case, we have the photovoltaic power plant with maximum installed capacity of 10 megawatts. With green line, here we have theoretically maximal energy production for this very specific day. So we have the daytime starting from 8 o'clock and finishing at 18 o'clock, so it's about 10 hours. In brown line, you see the actual value, and in blue chart plot, you see the day ahead forecast provided by the regression algorithm. So now let's try to make the analysis of actually what kind of quality metrics could be applied to the regression model assessment. Okay, so in the upper row, you may see the hours. So it's just the daytime starting from 8 till 18 o'clock. Then you have day ahead forecast presented in kilowatt hours, ground truth values, and here we have the very interesting outcome when calculating mean absolute percentage error. Well, that's actually what I was talking about, because when we have the predicted value greater than the ground truth, so the final error for these specific hours may be greater than 100%. So if we measure mean absolute error, so it's quite understandable as well, because it is measured in the corresponding units, kilowatt hours. So here we measure just the average deviation of the prediction from the ground truth. And here we have the average error in percentage of the model that you have created. And now, just imagine yourself being in the place of the company having such a software providing predictions of photovoltaic power plants output. Well, how would you feel if you would set that the error for the prediction of photovoltaic power plant output is 90%? Well, it sounds like even worse than random guessing. Yeah, and for this reason, it is obvious that mean absolute percentage error is not the best quality metrics for the problem under consideration. What I would like to draw your attention to is normalized mean absolute error. So what does it mean normalized? It means that we introduce some weighting, so we introduce some factor normalization to mean absolute percentage error, so which is actually calculated in a standard way. We provided normalization of the mean absolute error based on the results of the maximum theoretical power output of this very specific photovoltaic power plant. Let's consider the case when the forecasted value is lower than the ground truth value. So now you see how mean absolute percentage error changed. So all the values are lower than 100%, and we have the resulting error no greater than 29%, which can be considered as admissible for this very specific problem under consideration. But anyway, if we consider normalized mean absolute error, actually you can see the values, because when we are addressing normalized mean absolute error, it is not the case of calculating the error as it is, but it is the case of calculating the hypothetical weight of this error in the possible theoretical output of the specific photovoltaic power plant. So let me try to explain. Let it be 11 o'clock. So we have forecasted 413 kilowatt hours, and actual value is 562 kilowatt hours. For this very specific hour, I mean 11 o'clock, we have maximum theoretical power generation output of the photovoltaic power plant equal to, let it be, 5,000. So we just take the difference of 413 minus 562, yes, and weight it based on the maximum theoretical output of photovoltaic power plant in kilowatt hours. So this makes sense because from the point of view of the power system, it is not so important how you predict the error of this very specific small-scale photovoltaic power plant. But the idea of normalizing the mean absolute error gives you the opportunity to understand, so which share of theoretically possible maximum output you mispredict. So this is the general idea. Well, now let's consider the case with big deviations. As far as the blue charted diagram provides us with the predictions, and the brown curve illustrates the ground truth, so here we have the greatest deviation. And in this point, the theoretical maximum was actually achieved by the ground truth curve. Yes, so we have 9,000 of kilowatt hours. But the prediction provided for this very specific hour was about 2,000 of kilowatt hours. Let's move forward and look. Yep. So how it results. Well, let me check. So this very specific hour is, I suppose, 12. As far as our prediction was lower than the actual value, so we will never get this mean absolute percentage error greater than 100%. And for this very specific hour, the mean absolute percentage error equals to 76%. But let's see what happens at 8 o'clock in the morning. Oh God, absolutely, absolutely inappropriate. So at 8 o'clock, we have provided the prediction that it would be 300 kilowatt hours, but actual value was 15 kilowatt hours. And for this very specific case, very specific hour, we have the total error, which equals to about 2000%. I don't believe it. Anyway, please feel the difference. In this case, we've mispredicted the actual value of the photovoltaic power plant's output by about 6 thousandths of kilowatt hours. And for this, our misprediction was about 300 kilowatt hours. So, and what are we doing? We're penalizing the model for small deviation, and it completely distorts the overall accuracy of the algorithm. The application of normalized mean absolute error gives the opportunity to take into account both situations in a similar way, as far as we are considering like possible deviation, possible misprediction from the point of view of theoretically maximal power plant output. Well, now let's move to lecture learning outcomes. And within the framework of this lecture, we analyzed the concept of data, information, knowledge, and wisdom. And we found out that these terms are principally different, and nobody has to mix these terms either in professional area or during educational activities. We found out that there are many different types of knowledge, and this classification of knowledge helps the machine, the computer algorithm, to map the problem under consideration and even build the mental map of the challenge that we are aiming to solve. Each intelligence systems require preliminary data collection and pre-processing stage. It's like the very basics, because machine learning doesn't work if you do not deal with data properly. So if you do not provide correct, adequate pre-processing, you will never get machine learning model well worked. Magic never happens. Machine learning is an integral part of artificial intelligence, so please do not mix these terms between each other. What I would really like to stress and to emphasize in lecture learning outcomes is that the data set should be carefully allocated into training, validation, and testing sets, at least into training and testing sets. And the very specific case of the summer school project case, please be aware that if you include 90% of sunny days into the training set, you will train the model to predict sunny days. But actually, from the point of view of the physics of the process, sometimes you do not need the prediction model to forecast sunny days, because the energy output can be simply calculated. But the goal of the case, the goal of this subtask of the case, is to create the system which is capable to predict the days with abnormal weather conditions: rain, fog, snowstorm, sandstorm, low clouds, dead clouds, so whatever. So please be aware that bad day data should be included into the training set in order to train the system how to forecast these days. So be careful when selecting the quality metrics of your algorithm, because if you select inappropriate quality metrics, you will completely distort the training process. Moreover, you will not be able to provide adequate interpretation of the algorithm's operation. In some cases, inadequate quality metrics lead to like complete degradation of good machine learning models. For this reason, please be very careful when selecting regression quality metrics. Now the lecture is over. Thank you very much for your attention. I hope you find lots of useful outcomes, recommendations, and materials in order to make your project case solution better, stronger. So I wish you good luck and see you next time. Bye bye. It was Stanislav.